For decades, astronomers have been trying to figure out where in the world, or perhaps more accurately, where in the universe the heaviest elements such as gold come from. Now, new research based on a signal uncovered in archival space mission data may point to a potential clue: magnetars, or highly magnetized neutron stars. Scientists believe lighter elements such as hydrogen and helium, and even a small amount of lithium, likely existed early on after the Big Bang created the universe 13.8 billion years ago. Then exploding stars released heavier elements like iron, which became incorporated in newborn stars and planets. But the distribution of gold, which is heavier than iron throughout the universe, has posed a mystery to astrophysicists. It is a pretty fundamental question in terms of the origin of complex matter in the universe, said Anirudh Patel, lead author of the study published Tuesday in the Astrophysical Journal Letters, and a doctoral student of physics at Columbia University in New York City. In a statement, "It's a fun puzzle that hasn't actually been solved previously. The cosmic production of gold has only been linked to neutron star collisions. Astronomers observed a collision between two neutron stars in 2017. The cataclysmic clash released ripples in spacetime, known as gravitational waves, as well as light from a gamma-ray burst. The collision event, known as a kilonova, also created heavy elements like gold, platinum, and lead. Kilonovas have been likened to gold factories in space. It is believed that most neutron stars mergers occurred only in the past several billion years," said study co-author Eric Burns, assistant professor and astrophysicist at Louisiana State University in Baton Rouge. But previously indecipherable 20-year-old data from NASA and European Space Agency telescopes suggests that flares from magnetars that formed much earlier, during the infancy of the universe, may have provided another way for the creation of gold. Burns said, "We don't yet know if magnetars played a significant role in the production of gold in the early universe," he added, "but we hope to test this with upcoming missions in the near future." Quakes on stars. Neutron stars are the remnants of the cores from exploded stars, and they are so dense that 1 teaspoon of the star's material would weigh 1 billion tons on Earth. Magnetars are an extremely bright type of neutron star with an incredibly powerful magnetic field. Astronomers are still trying to work out exactly how magnetars form, but they theorize that the first magnetars likely appeared just after the first stars, within about 200 million years of the beginning of the universe, or about 13.6 billion years ago, Burns said. Occasionally, magnetars unleash a bonanza of radiation due to starquakes on Earth. Earthquakes occur because Earth's molten core causes motion in the planet's crust, and when enough stress builds up, it results in volatile movement, or the ground quaking beneath your feet. Starquakes are similar. Neutron stars have a crust and a superfluid core, Burns said in an email. The motion under the surface builds up stress on the surface, which can eventually cause a starquake. On magnetars, these starquakes produce very short bursts of X-rays. Just like on Earth, you have periods where a given star is particularly active, producing hundreds or thousands of flares in a few weeks. And similarly, every once in a while, a particularly powerful quake occurs. The researchers found evidence suggesting that a magnetar unleashes material during a giant flare, but they didn't have a physical explanation for the ejection of the star's mass, Patel said. It's likely that the flares heat and eject the crust material at high speeds, according to recent research by several co-authors of the new study, including Patel's advisor Brian Metzger, a professor of physics at Columbia University and senior research scientist at the Flatiron Institute in New York City. They hypothesized that the physical conditions of this explosive mass ejection were promising for the production of heavy elements, Patel said. Tracing a stellar signal, the research team was curious to see whether there might be a connection between the radiation from magnetar flares and the formation of heavy elements. The scientists searched for evidence in wavelengths of visible and ultraviolet light, but Burns wondered whether the flare might create a traceable gamma ray as well. He looked at gamma ray data from the last observed giant magnetar flare, which appeared in December 2004 and was captured by the now retired International Gamma Ray Astrophysics Laboratory, or Integral, mission. Astronomers had found and characterized the signal, but did not know how to interpret it at the time, Burns said. The prediction from the model proposed by Metzger's previous research closely matched the signal. From the 2004 data, the gamma ray resembled what the team proposed. The creation and distribution of heavy elements would look like in a giant magnetar flare. When initially building our model and making our predictions back in December 2024, none of us knew this signal was already in the data, and none of us could have imagined that our theoretical models would fit the data so well. It was quite an exciting holiday season for all of us, Patel said. The researchers also used data from NASA's retired RHESSI, or Reuven Ramadi High-Energy Solar Spectroscopic Imager, and the WIND satellite. All of the data supported the team's findings. Long-term federally funded research enabled the discovery, Burns said. It's very cool to think about how some of the stuff in my phone or my laptop was forged in this extreme explosion over the course of our galaxy's history, Patel said. Dr. Eleonora Troja, an associate professor at the University of Rome, who led the discovery of X-rays emitted by the neutron star collision in 2017, said the evidence for heavy element creation from the magnetar event is in no way comparable to the evidence collected in 2017. Troja was not involved in the new study. The production of gold from this magnetar is a possible explanation for its gamma-ray glow, one among many others, as the paper honestly discusses at its end, Troja said. Therefore, I wouldn't go so far as to say that a new source of gold has been discovered. Rather, what's been proposed is an alternative pathway for its production. Troja added that magnetars are very messy objects. Given that producing gold can be a tricky process that requires specific conditions, it's possible that magnetars could add too much of the wrong ingredients, such as an excess of electrons, to the mix, resulting in light metals like zirconium or silver rather than gold or uranium. However, one cannot exclude that they might also produce the right conditions locally somewhere, albeit in a very small volume. So observations of more events will be needed to understand their role in the nucleosynthesis of heavy elements, she said. The researchers believe that magnetar giant flares could be responsible for up to 10% of elements heavier than iron in the Milky Way galaxy. But a future mission could provide a more precise estimate, Patel said. NASA's Compton Spectrometer and Imager mission, or COSI, expected to launch in 2027, could follow up on the study's findings. The Wide Field Gamma Ray Telescope is designed to observe giant magnetar flares and identify elements created within them. The telescope could help astronomers search for other potential sources of heavy elements across the universe, Patel said. In the meantime, the team is eager to continue searching for answers. We're trying to figure out what the early universe was like by looking at what it is doing today, Burns said. The universe is very much like a movie that starts in the beginning and ends at the present day. We just happen to be living in the middle of it. Thanks for watching this episode. If you'd like to help support the channel, you can do so through the link in the description below.